So I got a complaint from Alex after last week's lecture. Different Alex, by the way. Amazingly enough, I did not get any complaints from Alexander Grossman after last week's lecture. And so, with Grothendieck's evidence tacit approval, I will continue telling the stories that I've been telling, which, in a way, is my answer to Grothendieck's peculiar question that I mentioned last time. Yes, what is a meter? And in a way, these lectures that I'm giving are my answer to that question, or rather, these lectures are my answer to the question that I like to imagine Grothendieck was really asking, which I imagine is something like, what is the relationship between dimensional analysis and the foundations of algebraic geometry and perhaps of physics? And well, anyway, as I was saying, I got a complaint from Alex after last week's lecture, and that's sort of neither Alex is here right now. But Alex Hoffman's complaint was that, and I really agree with this complaint, was that just a lack of clarity in my attempts to explain and give examples of doctrines and the things in the doctrines, the theories, the interpretations of theories, and the morphisms between interpretations. And I think one big reason for the lack of clarity was my failure to take advantage of a very useful technique for pictorially representing theories and interpretations and morphisms between interpretations. And that very useful technique is called the technique of sketches. And so that's something that I'd really like to talk about right now. So let me try to tell you what sketches are. So basically, the method of sketches, the technique of sketches, it's really roughly the same idea as the technique of commutative diagrams, which is a way of pictorially representing things like categories and functors and natural transformations. Sketches is like a fancier version of commutative diagrams. And so let's just remind ourselves of what's the basic idea behind commutative diagrams. Well, so in category theory, we have categories, and we have functors, and we have natural transformations. And this pattern of having these three things in a sort of hierarchy, that's a pattern that gets repeated in lots of different two categories, besides the two category of categories. I guess these are like the 0 cells, 1 cells, and 2 cells. And a way of pictorially representing these things is that you can sort of draw a category as what's called a diagram scheme. And you represent a functor as a commutative diagram, something I just called a diagram. And then you represent natural transformation by, I guess, what I would call a prism diagram. And let me say a little bit about what these things mean. So, computer diagram is, something that looks like that, something like that. So like nodes and arrows, or maybe letters and arrows, and the arrows stand for morphisms, the nodes stand for objects. There's some implied, usually culturally implied commutativity conditions, like you go this way, do that. And so the actual diagram is representing a functor, but the sort of abstract shape of the diagram, that's what's called the diagram scheme, and that represents the category. So a diagram, how do I say it? You can say that a functor is really a diagram that's shaped like the diagram scheme given by the domain category. And then the actual concrete things that appear in the diagram are objects and morphisms of the codomain category. That's the basic idea of diagrams. Diagram schemes for the categories, diagrams for the functors, and prism diagrams for the natural transformation. So a prism is, like, if you have another one of these diagrams, diagrams of the same kind, then you can have a natural transformation between them. That's kind of a prism shape. And again, part of the idea of this prism is that there are all these naturality squares or naturality parallelograms or whatever it is. Draw that prism? Yeah, I start these sort of prism shape.
Is this like taking a representation of a quiver, like taking a quiver and mapping it into the category?
Yeah, I mean, a category is a certain kind of quiver with something extra.
Right.
And so you can draw a category as a quiver, and the extra is kind of like taking for granted. You can apply commutativity conditions and stuff like that. And so, yeah. So this is something we pretty much all know about using diagrams to represent these kinds of things over here. And the idea of sketches is just a fancier version of this, and the only thing that's really fancier about it is just that instead of depicting plain categories and plain functors and plain natural transformations, you're depicting some kind of fancy categories, fancy functors. And so for example, the categories could be fancy because they could be monoidal categories. They could have a tensor product or something like that, which is the kind of thing happens in some of our examples. Our doctrine of dimensional categories. Dimensional categories are really, they have a tensor product, which is kind of monoidal category. And really that's just going to mean things like that in the pictures there are going to be symbols for tensor products and things that are going to be showing up. This whole idea of sketches, you could probably develop it in a very formal way, or you just do it in a sort of an informal way. And I'm definitely leaning more in the direction of doing an informal way. So we're not going to worry about, technical details of how to draw, of sketches of actual mathematical objects themselves. We're just using this convenient way of drawing the things that we're interested in, which are these categories of some special kind, like dimensional categories, dimensional functors, and dimensional natural transformations, which I guess, so in the language of doctrines, that would be theories and interpretations or models and morphisms of models. So I want to go ahead now and do a bunch of examples of using sketches to depict and understand theories and models and model morphisms of a doctrine, in particular, mainly right now, of the doctrine that we're focusing on, the doctrine of dimensional categories, where the theories are the dimensional categories, the models are the dimensional functors, and the model morphisms are the dimensional master transformations. So, let me try that now. So, I'll start with the same high-order example that I've been doing, which previously I've been drawing it by drawing a sort of grid of objects in the dimensional category. And I guess the dimensionless dimension is there, and the mass dimension is there, and the velocity dimension is there, and the momentum dimension is there, the energy dimension is there. The dimensions form an abelian group under multiplication of dimensions, or you can call it tensor product of these dimensions or these line objects. And then we have the quantities within the dimensions, like mass of particle A and mass of particle B, and the initial velocity of A, initial velocity of B, final velocity of A, and final velocity of B, and then some relations, which you think of as sort of commutativity conditions, conservation of momentum and conservation of energy. But now let's try to, instead of using this method of drawing things, let's try to use the method of sketches. So, it's going to look like this. It's going to look like that's almost it. That's almost the whole sketch of the theory. I kind of left out the conservation laws, the implied commutativity laws, but I left them out here, pointing to that too. You could try to incorporate into the sketch somehow, you know, conservation of momentum, conservation of energy. You would get horribly baroque if you tried to draw it in, but principally you could do it. But I don't really want to, because that's not really what the sketch method is really supposed to help us with. This is a picture of the theory. This is a this theory with the conservation laws. Another way of drawing that theory is that this is the diagram scheme. This is the abstract diagram scheme. So we don't call it a diagram. We call it a diagram scheme. Diagram scheme means that it's a plan for a diagram, but it's not really filled in. You might think these are labels, but these are really like this, mass and velocity. Those are really just abstract labels. They haven't been filled in with concrete labels yet. And again, we put abstract labels here, like mass of particle A and mass of particle B, initial velocity particle A, initial velocity particle B, final for A, final for B. You put those abstract labels in, but those aren't yet concrete labels. This is just a diagram. So a diagram, this is the diagram scheme. So the diagram is when you make this into a concrete thing. You get rid of these abstract labels and you put in the concrete labels for the objects and morphisms in the environment that you're interpreting the theory into. And that's what, so I think that's what the method of sketches is really good for, is not so much for drawing the theories, but for drawing the models and for drawing the model morphisms. So you can really get a good idea of what the models are like and what the model morphisms are like. So let's try some examples here. So we need an environment to interpret our theory into. Let's use the line, the environment, the dimensional category of lines over our favorite field F. We'll call field F. So can anybody give me an idea of how to start to interpret this theory? Right, we're going to draw a diagram that looks like this abstract diagram. But we're going to use actual one-dimensional vector spaces, actual linear operators between them. Anybody have any suggestions for what I should?
Come on, it's almost the unit.
Oh, here for one.
What's the unit?
Yeah. And so what's another name for? So we're going over field F. What's another name for the unit under tensor product?
Yeah, the field itself.
Yeah. So that could be F. Or maybe, I don't know, you could call it F to the 1, but everything could be one-dimensional for us. Let's say F. What about these other dimensions, these other abstract dimensions? What are they going to get realized as, perhaps?
They're also there.
Yeah. I mean, you might be able to find some other one-dimensional vector space somewhere, but that wouldn't be much point to that. So it's sort of a harmless restriction if we insist. Probably harmless restriction if we insist that all of the one-dimensional vector space is actually just the standard one-dimensional vector space. So there wasn't much interesting choice involved so far, but we get more interesting choices when we pick the concrete realizations of the abstract quantities. So these are going to get realized as one-by-one matrices. One-dimensional vector space, one-dimensional vector space, linear operators, one-by-one matrix. It's really just a number living in the field F. So, I don't know, let's say, for example,
1,836.
what is that? Oh, that's
The mass of the proton.
Oh, you might do that.
Electron.
Okay. So Tom's suggesting that A be an alpha particle and B be a beta particle? No. Have A be a
Electron.
A be an electron and B be a proton, something like that.
So 1 and 1,836. Come on, you wanted a number, I think.
Yeah, but I already picked, I didn't solicit none of the things. I'd already picked out.
Oh, you do have a number?
Yeah, and it's slightly different from your example. My example is much silly. John gave a semi-realistic example. Oh, okay, John. Oh, mine would be silly.
Okay.
Mine would be, let's say, 3. Random figure over here, and 0. So mine actually involves a massless particle of mass 0, which is a little bit peculiar. I mean, I guess that shows up in relativistic physics a lot, and it's not anything terribly unusual there. But here we're doing more like classical physics, and it seems a little bit weird to think of an example of 0 mass here. But that's the theory we created. You know, if you think this is a stupid theory, where you allow particles of 0 mass, well, you could have created a different one.
You need a different doctrine to rule out.
No, you wouldn't. You just put in an inverse to this quantity, and that would and that would force this quantity to be an invertible thing, and that would rule out the possibility of 0. So that would be changing the theory. We'd be staying with the same doctrine, but we'd be changing the theory. And that might be a sensible thing to do, but that's not what we're doing right at the moment. We're keeping this option of having particles of mass 0. And so according to what we wrote down for how conservation of mass and conservation of entity work, even in the case where one of the particles is 0, can somebody tell me what would be, some possible velocities that would satisfy the conservation of momentum and conservation of energy?
We get the same velocity for all 4 arrows.
That would work, yeah. I think the really important thing is that since this is a particle of all mass, it had better not change its velocity at all, I think. All right. So where's that? That's these two, is that what you're saying? So it's like, 6 and 6. Or something like that. But the other one can pretty much bounce around as much as it wants. That's not gonna. So it could be like, 3 and negative 10 or something like that. So that's just the way it works in this example. So that's a model of the theory. Let's see if we can come up with another model of the theory and a prism that constitutes a dimensional natural transformation. I guess, of course, you take the exact same one and you have the identity natural transformation, but that would be boring. So try to do something a little bit less boring than that.
Let's have them both have mass.
Say it again?
Let's have both particles have mass this time. Or you can't even do that, I guess. That's a good question. You can't even do that.
Yeah, you have to think about what are the rules. So,
Yeah. No, that's true.
in fact, is there any way to put, if we had both non-zero things here, is there any way to put these things? There probably is.
Yeah, no, this is a sort of, let's see.
Well, it isn't going to work, though. In the end, it's not going to work because, I've never really given a precise definition of what a dimensional natural transformation is. If you really want a precise definition, remember that dimensional categories are a certain kind of symmetric monoidal category, and people have this definition of what the people have this definition of what a symmetric monoidal natural transformation is, and that's what we use.
So it appears you can do that, but you have to use all of the mass in the natural transformation also.
Say that again?
It appears you can put mass on those particles, but in order for everything to be in the prism,
Yep.
you would require the 3 arrows all to be zero. All 3 arrows would force be during the natural transformation, because then you don't have any.
Yeah, and that's ruled out by
Yeah.
And that's
being a
symmetric.
symmetric.
Yeah, that doesn't, so that.
Yeah, so in terms, basically, being a symmetric monoidal natural transformation is basically going to mean that when you assign these, so remember that we're going to have a prism, we're going to have things like this. So to each object, we're assigning really another 1-by-1 matrix. And basically, if you look up the definition of a symmetric monoidal transformation, it basically says that this assignment of these numbers that we're going to pick here, that basically has to be, in this context, it has to be a homomorphism from the objects under tensor product to, well, in this case, to numbers. So this is the identity element. Right, and this is the identity element. This is the unit object. So if it's going to be homomorphic, I have to take the unit object to the identity element. So the scaling here has to be 1.
So that I think eliminates the need for now something harder.
Yeah. So I think it forces us to put 0 over here. Just like this is 0 over there.
Yeah, you have to convince yourself that that other arrow on that top square can't be 0.
Okay.
And that's because you actually have a dealing group of objects. So that's being convertible.
This one here?
That one there.
Yeah. Yeah. Can this one be 0? No. This one cannot be 0?
No, if you force this one in there.
No,
Right,
not
yeah.
because of-
That's right. So, yeah. So this would have to be, I guess this could be almost anything else, though. It could be, for example, 9 or something like that.
Okay, well then that other arrow has to be 9.
It has to be 3. Yeah, for this 1 times 9 equal to 3 times 3. Yeah. So do you see what's going on? It's like, this is the coordinates, the coordinates of a point on the projective line, a so-called homogeneous coordinates of a point on the projective line. 3, 0. this, particularly this, is a rescaling transformation. And it changes the homogeneous coordinates from, it multiplies all of the coordinates by 3. Instead of being 3 comma 0, it's like 9 comma 0. So it's different coordinates, but it's representing the same points on the projective line. And that's, so that's how the dimensional matrix transformations correspond to the way that homogeneous coordinates of a point in projective space can be rescaled. And so what about down here? Can we give a suggestion about how we can do something down here?
I think we what we need to do is just choose the bottom morphism and that'll force the velocity.
Yeah, we're gonna like 10 or something like that. And that would force all these numbers to get multiplied by 10. All the velocities are getting rescaled. So like we're like choosing a new unit of velocity that's like 1/10 of what the old unit was. And so again, these 4 couples of numbers, they represent the same point in a certain projective 3 space. So this is supposed to help in understanding how this business works, how you can think of the model of the theory as really supplying the homogeneous coordinates of a point in, well, in this case, in a multi-projective space, a Cartesian product of projective spaces. And then the morphisms between the models, in particular the isomorphisms between the models, are saying that certain homogeneous coordinates are equivalent to certain other homogeneous coordinates just by rescaling.
All the morphisms are isomorphisms.
Say that again?
All the morphisms have to be isomorphisms.
Yeah, you can prove in this particular doctrine that all of the model morphisms are isomorphisms. And it basically has to do with the fact that all of the objects in the dimensional categories have inverse objects. And that somehow forces the model morphism to be convertible. So, okay, so that's just an example of how it works. So now let's try some other examples. So I'm going to sketch another theory. We're working the same doctrine of dimensional categories. I'll sketch another theory. And I guess I already, at the end of last time, I actually started sketching this theory, even before I introduced another sketches. So this is going to be well, I guess I'll just go ahead and sketch the whole theory right now. And then maybe we'll try and do some verbal descriptions of the theory. So, and that's pretty much it. That's going to be the whole sketch of the theory. In this case, there's 3 arrows right here. So that's actually a changeable parameter. You can make it pretty much any number of arrows you want. And that's the sketch of the theory. And in this case, it really is a complete sketch. So there aren't supposed to be any implied communication conditions or anything like that. This is a very vanilla sort of example. So So this is what the prototype model looks like, right? The theory, the sketch of the theory is sort of the sketch of a prototype model. A diagram scheme is a prototype for a diagram. It's not an actual diagram. This is just our prototype for a model. An actual model is where we actually flesh this out. So once again, let's work in our favorite environment, one-dimensional vector space over our favorite field, F. So the model is going to end up looking like this. Some specific linear operators, some specific numbers, really, scalars here. I don't know.
Until you specify them, they look.
What?
Until you specify them, it's a lot like you.
Right.
Some specific ones, I'm not going to specify.
Right. If you give a non-specific example, you didn't really give an example. So can you say what the moduli space of models of this theory is like? Let's see, we should also draw a prism diagram. So we have another one over here. Prism point up this way. So remember, this is the unit object, so this scalar has to be 1. But the other one, the scalar here, the rescalar, the rescaling transformation, can be anything. But basically, you have an abelian group of dimensions, and the independent dimensions can get independently rescaled. And the trivial dimension is not an independent dimension, so it's not allowed to be rescaled. It has to stay the same. If you're not, in this game, you're not allowed to rescale the dimensionless number. You're not allowed to choose a new unit of dimensionlessness.
There's a joke in physics.
Yeah.
You say, choosing dimensions, choosing units where pi equals 1. So you try to, you don't want to worry about factors of pi.
Oh.
You know that you're not allowed to do that.
Okay. Right, yeah, you can try it. Right. In this particular game, it's actually completely illegal to do that.
Wouldn't it be P2?
Say it again?
Wouldn't it be P2?
Yeah, this is the projective plane. So you can put any, well, again, in fact, because this object is invertible, you have to choose an invertible rescaling here. So again, it could be 5 or something like that. And that would force these numbers get multiplied by 5. So, we already sort of commented on this example in the fact that, this is the projective plane.
With that one extra point, right?
Yeah, that's right. What's the one extra? Let's throw the one extra point, the one that's not really supposed to be there from an algebraic geometry point of view. That would be this model. There's nothing prohibiting that in our rules. That's not an official point of the projective plane. So really, our moduli space is some sort of extended projective plane that includes this one extra point that perhaps we don't really want. But that's the way it is. So this is a really basic example, obviously. But there's a particular point that I want to make about this example, which is that our way of thinking of it really connects with one of the standard ways that algebraic geometers like to think about projective space. So the slogan that algebraic geometers use to describe projective space, let's say, for example, the projective plane, is they say that the projective plane is the classifying space for line bundles generated by 3 sections. And in understanding what algebraic geometers mean by this, instead of being very directly related to what we mean when we say that you sketch the theory like this. I mean, they're saying the same thing, secretly. I mean, there's the line bundle right there, and this is a picture of 3 sections of a line bundle. Sections are morphisms from the trivial thing. You can call them points if you want, kind of like a thing with 3 points. And so we really like to understand. I mean, again, this is just a little tiny tip of an iceberg. This is the beginning of a story that algebraic geometers learn and tell each other about. It's really very much the same as the beginning of our story here. I mean, so we really are telling the same story that they're telling, but that's in a somewhat different language. There's a lot of things I do understand here, and a lot of things that I don't understand here. I'd like to comment a little bit on some of the things that I do understand, some things I don't understand. This word classifying space, I would say that I think it's pretty much a synonym for moduli space in the world of algebraic geometry. I would think it's really just another word for moduli space. Although I won't guarantee that algebraic geometers don't have some subtle difference in meaning between them. But on the other hand, this word classifying space, I personally was much more familiar with the use of the terminology classifying space in homotopy theory than in algebraic geometry. And I was more familiar with it there, but I understood it a lot better in homotopy theory, a long time before I understood what people were talking about in algebraic geometry. And there's some funny relationship. There's some funny relationship between the way the terminology classifying space is used in algebraic geometry in this kind of situation, where algebraic geometry is saying something like that. There's a funny relationship between this usage of the terminology compared to the usage of the terminology in homotopy theory.
Can you say what the algebraic geometers mean by this sentence?
They really mean what I'm saying here, that every space is a moduli space of models of a theory. What?
Yeah, okay.
Every space is a modularized space of models of a theory, and I've sketched the theory here, that the projective plane is the modularized space of models of. And this is the way algebraic geometries say the same thing. But there are some funny things about it. Perhaps there are some things that you're complaining about?
Well, they do use the phrase modularized space.
Yes.
And they would never say, for example, that P2 is the modularized space for line bundles generated by 3 sections.
No, that's not completely true. There's a set of notes from the MIT course on, I don't know, understanding moduli spaces or something like that in algebraic geometry. And that set of notes starts with the example of projective space in this way. So again, I mean,
Okay, they usually seem to talk about modularized space of structures on a given fixed. Well,
yes, but you can secretly interpret that way as well. I mean, this.
so, yeah. Well, I'm just
Yeah.
probably like you. Now got me wondering what they mean when they say classifying space.
Well, they probably mean several different things. But one of the interpretations of what they mean is that it's really a modularized space of models of this theory. But one of the things.
That makes sense, but it sounds more like what you mean. I mean, maybe
No, but
none of them would ever say that, so I'm just wondering what they would say.
they might not say it out loud, but that's usually what they're thinking, some of the time, some of them. And in particular, I mean, so, because I think the point is that they really are doing some sort of multi-level thinking, and us outsiders are only catching part of what they're thinking some of the time. And there's something, that they don't explain to the outsiders very well, and it's this other level that they're thinking on they're thinking on several levels at the same time, but they're not really letting us know about it. But this is really part of what they think. One of the things that's funny about the way they say it is that this way of speaking in the English language, it sounds like these 3 sections are very anonymous. It sounds like they've been existentially quantified over. Whereas in our theories, these are you should really give them specific names. There's 3 specific sections, A, B, and C. And it's very important to keep track of them. I mean, it's only by keeping track of them that you can manage to detect the difference between different points in the projective plane. So, one of the things I'm basically trying to suggest here is that sometimes it's sort of decategorified language, and it seems to be some sort of tradition in algebraic geometry, particularly when they're doing this sort of multi-level thinking, that they give natural language descriptions of a space in a sort of decategorified way, and you're actually supposed to know that you're supposed to categorify it in order to really create the fancy characterization of the space.
So by decategorifying, you mean, sounds like they're talking about the property of being generated by 3 sections.
Exactly. That is the property.
Structure.
Exactly. Being generated by 3 sections is just a property. And that doesn't really capture what's really interesting about the projective plane, which is that it's really not about the property of being generated by 3 sections. It's really about the structure of being equipped with 3 sections, 3 specific sections, A, B, and C, which then serve as give you the homogeneous coordinates of a point in the projective plane. So So that's a little bit of my attempt to psychoanalyze what algebraic geometers are doing. And I'm doing this from a greater distance than you are, because I probably have interacted with them less than you do even. So, you know, in no way trust me as an expert on the culture of algebraic geometry. I'm just an outsider trying to figure out what the hell they're talking about. And this is my best attempt to understand what they're talking about. And my best attempt to understand what they mean when they say things like this. What they really mean when they say something like this. Deep down, what they really mean is they mean this. That the projective plane is the moduli space of models of this theory, this dimensional theory, this dimensional category. And if you put this into the language of graded commutative algebras, it's saying that the projective plane corresponds to a graded commutative algebra. It's graded by the abelian group Z, just a one-dimensional abelian group, just the tensor powers of this single object F. And it's a graded commutative algebra, and it's got three generators in grade 1. And that's the graded commutative algebra that corresponds to the projective plane. So, yeah, so my basic point was supposed to be that the way that algebraic geometers use the terminology classifying space, it has some very important relationships to the way that homotopy theorists, for example, use the terminology classifying space. But there's something deeper about the way that algebraic geometers are using the terminology. No, Thomas not quite agree with me on that. There are deeper ideas in the way that algebraic geometers are using this terminology. And so I guess the point is you have to be careful in relating algebraic geometry to homotopy theory. It's really interesting to do so, but you have to take into consideration certain differences in culture and certain ways in which what's going on in algebraic geometry may be more complicated, more interesting than what you might have thought was going on if you were just guided by your homotopy theory intuition. I mean, I thought the whole concept of line bundles and sectional line bundles, I thought it was, you know, a really trivial thing back when I thought of it as just part of homotopy theory. But when I started thinking of it as part of algebraic geometry, I realized that there's a lot more to it. It's based on some very simple ideas, but it leads to some very interesting places. So I want to do more examples here. I'm going to do another example of the dimensional theory, and we'll think about its moduli space of models. So so the example that I want to do now, the point of this next example is that it's supposed to give you a better flavor, or at least perhaps a different flavor of an example of a moduli space. An example that's more like a certain flavor of example that shows up a lot in mathematics. I mean, an interesting moduli space is a moduli space of interesting things. And whereas some of the examples that we've been looking at, the models seem like rather contrived objects or something like that. Actually, in the next example, the models will still be contrived objects, but they'll be on the way to being objects of some familiar kind in mathematics. Well, I better just do the example so I should quickly explain what I mean by that. So, this is the example that I want to do. I want to do the moduli space of moduli space of n tuples L1 through Ln of lines equipped with a Lie algebra structure on the direct sum L1 direct sum direct sum Ln. So in this example, I started out with sort of verbal description of the moduli space that I'm aiming for. But then we'll try to interpret that, we'll try to convert that into, I guess, into a sketch of a theory. We'll try to convert that into a sketch of dimensional theory. And again, part of the point of this example is that Lie algebra, that's an example of the kind of thing that mathematicians actually care about. You know, they'd like to know some moduli space of Lie algebra or something like that. Now, our example is a little bit contrived because we're not just going to be classifying Lie algebras, we're going to be classifying Lie algebras that are equipped with an extra structure amounting to splitting the underlying vector space up into lines. It's a little bit contrived, it's not that contrived. And it's necessary for the situation we're in at the moment because our theories only deal with one-dimensional objects. Our theories have to do with kinds of structure that are carried by one-dimensional objects or bunches of one-dimensional objects. And so that's kind of, you know, we're restricted to saying things like this at the moment. But let's go ahead and try to understand this. So,
it reminds me a little bit of what Lie started out trying to do. What Lie was trying to classify Lie algebras at first. He said something like, I'll classify the one-dimensional ones and the two-dimensional ones,
right,
and the three-dimensional ones. Although he may even have been doing something a bit more like what you're doing. Because
Yeah.
I classify them by means of looking at the structure constants and trying to find the solutions to this equation. So that's picking a specific basis. So it's a bit more like a graph.
I don't really know enough about, I've read a little bit about that, but I don't remember exactly, so I don't know how it was fitted. So, any ideas on how to sketch this theory, any idea how to sketch a theory that would, you know, fulfill this idea that this is the moduli space that we're trying to look at as a moduli space of models of one of our theories? Any ideas on how to sketch this theory? So a sketch, what is the sketch part? The sketch is, I guess officially maybe the diagram scheme. And
So you'd like to write down the lead bracket operation.
yeah.
But
That's the structure. The structure is the lead bracket operation. Again, we're doing this very informally. There are no very hard and fast rules about how we're supposed to draw the pictures. It's just a convenience for us. So, are you getting some idea about how to?
Well, I was
Trying to get something else.
trying to get something else to do, but, yeah.
Well,
So
how
to start
about
out-
that? Yeah.
Choices of the exterior power, the second exterior power.
Say that again?
Is choices of the second exterior power over the space that you're working on? Choices of
I think that's
Second exterior power has to do with where the bracket lives, kind of? Yeah, I can think it's that way.
I mean, the way I was,
Yeah.
trying to get other people to do it.
Yeah.
is that You want to write down the lead bracket operation, and that whole big fat thing tensor itself to itself.
Yeah.
But that's against some official rules, because you're only supposed to talk about one-dimensional vector spaces.
Right, but since we're allowed to make up the rules as we go along, what you're suggesting is actually legitimate, because even though we're drawing sort of higher dimensional objects here, so this is an n-dimensional object. In fact, maybe we should already specialize to some nice low case of n, like n equals 2 or n equals 3 or something like that. In fact, let's try that right now. Let's try the case of n equals 2. So we have L1 plus L2. Right, I mean, as John is saying, in this description or in this verbal description, it sounds perhaps like you're violating the rules of the doctrine. The doctrine says that you can only talk about one-dimensional objects, line objects. And this direct sum is not a line object, but we can get away with it on an informal basis, because sometimes these higher dimensional direct sums are virtually there. Think of them as like extra virtual objects. Because the point is that the morphisms between them just get encoded as matrices of morphisms between the one-dimensional objects. So that's why you can get away with thinking about pretending that these higher dimensional objects exist. So just the ones that are direct sums of the line objects that you have. So in that spirit, can somebody describe? That's a direct sum. Can anybody describe a more fleshed out version of this? I mean, this just looks like one big lump, a single arrow from this complicated thing to this complicated thing. But can anybody convert it into something that is more legitimately part of the lines doctrine? That really gives us an idea of how much structure, what linear operators are involved between the line objects that we have.
So you'd have, for example, the portion of L1 times L2 that goes into L1.
Yeah, basically you just expand this out into kind of distribute the tensor product of the direct sum, and that'll give you a direct sum of lines, and then that's more direct. So let's just try this. We're just distributing the tensor product. We get L1 tensor L1 plus L2 tensor L1 plus L1 tensor L2 plus L2 tensor L2. And that's mapping to L1 plus L2. So it's going from a direct sum of 4 lines to a direct sum of 2 lines. So it's sort of like, in my calculation, it would be like a 4 by 2 matrix. And so the lead bracket operation amounts to 8 things like there, which let's see. So okay, well we can try and continue sketching. So I guess along the lines of what John Werner was suggesting. I mean, this corner of the matrix, we just isolate that. That's the thing that goes like this. Right, so there's going to be a thing like this. And so what else are we going to have?
Or we're going to have a bunch of other things, but even already for that thing, if we're smart, we can save some work.
Okay, right. You can try and be a little bit efficient by thinking about constraints that are hidden in this description, because the Lie algebra satisfies some rules about anti-symmetry and Jacobi law, things like that. So what efficiency are you suggesting here? That, yeah, so,
Make some of these other things.
Yeah.
It's 0.
It's 0 because of some anti-symmetry, I guess, that are alternating, sometimes called the alternating law.
Yep.
So,
So we don't really need to even mention it if we're feeling.
yeah, we don't really need that one. We don't really need that one. So yeah, I just kind of cross that one out there, or put 0 there. Oh, and click target also applies there as well, that whole column. Sorry.
That's right. So your 2 columns get killed.
Yeah, and then the last one.
Okay. And any other,
Sure, yeah, there's even more.
what's the word I'm looking for? Any other redundancies that get eliminated, or?
Well, also the anti-symmetry should give relations between some of these possibilities.
Yeah. So,
Sure, 2 free variables.
Yeah, so if you know one of the remaining columns, you see the other one is just minus that. So
okay, so it's like X and Y and negative X? Negative Y, is that what you're saying?
yeah.
Like that? So really, the independent data consists of things that go, let's see. Okay, first of all, from L2 into L1, and there's one going to L1, and then there's one going from L1. So that's what we've got. That's what we've gotten it down to by starting out knowing that we wanted a bilinear map, but then the anti-symmetry, the alternating law, got us down to just this. And then the only thing left that we have to worry about is the Jacobi law, is that right? Is that what it's called?
I said Jacobi.
Jacobi, okay.
Identity.
The Jacobi identity, okay, that's what I'm talking can anybody say anything about that, about the Jacobi identity? Is that going to give us a relation here? What kind of relation is that going to give us? Is it obvious? Is this easy to figure out?
To me, it's easy to figure out if I call the, make up names of elements of L1 and L2. And like,
You're allowed to do that.
yeah, I'll call like A and B. And then I write down different Jacobi identity. Write down the Jacobi identity and stick in some A's and B's in it. See how many. I could put A's and B's in lots of different ways, but probably most of them are not all that different.
Yeah, I mean, well, basically what's going to happen, what John's alluding to, is, if you just look at the Jacobi identity, you can see that it has a lot to do with kind of three things, and it really, it's almost obvious that it's, I guess, just vacuous or something, or irrelevant or something like that for the case where the three things that you're plugging in have some sort of linear dependence between them. Is that right?
Probably, yeah. But I was saying could make it, if you just like write it down, write down the Jacobi identity, but only use letters A and B.
Yeah.
See what kind of things.
All right, let's just test that. Let's test that. So it says what A? Right. There's the cyclic version of the.
But everyone can remember
there are different versions people use. I'll just use the cyclic one, which is the one I don't like. So I'll use it.
Then you always some B against that.
Sure. But am I doing the cyclic one? That is really the cyclic permutation that I'm performing? Yeah. Okay. But now John is saying to have C be the same as B. And I guess I'm hoping that this just becomes vacuous now. Something like that. I think that's right. So this one just vanishes, and the others
True by ancestry.
are true by induction. That's right. Yeah, that's right. So it really is vacuous, and I think that if we didn't screw up, I really think that means that Jacobi identity is vacuous until you get up to n equals 3, and then it's non-vacuous. So I think that means we actually finished the whole sketch right there. That's a sketch of this theory. So that's the theory right there. It's actually a little bit fun, but if you get for n equals 2 and n equals 3, etc., to actually figure out what the moduli space is like here. I guess I'm going to mostly leave that as for fun exercise, I guess. But let's go ahead. Let's do just. Let's convert this into a graded commutative algebra, right? So we have this equivalence between dimensional categories and certain kind of graded commutative algebra. Let's just see what this looks like as a graded commutative algebra. So first of all, can maybe say what should it be graded by? Yeah.
5 minutes.
By what?
5 minutes.
Okay. What should this be graded by?
B squared.
It should be graded by b squared because why? Because of the fact that we have two independent line objects, two independent dimensions. So guess I'll draw a little grid again. And I guess I'll put the identity element right there. And I guess I'll put like L1 right there, L2 right there. So, we'll just randomly call this X and call this Y, is that what we called it before? Yeah. How do we express this as a gradient commutative algebra? This is the sketch version of the theory, but how do we, just for exercise, how do we interpret this as a gradient commutative, a presentation of a gradient? So a sketch of a dimensional theory can be converted pretty easily, it seems, into a presentation of a gradient commutative algebra. So, well, first of all, we set up the grading C squared, but now we're going to put the generators and relations.
You use the fact that the monoidal structure is a group to move the objects over to one side, so that you just have dimensionless into some grade.
That's right. That's right. That's right. So how do you move?
Take that morphism tensor with L2 inverse.
Yeah. Yeah.
Identity morphism on L2.
Yeah. So you can say.
I'm sorry, you didn't say that.
You didn't say that? Well, but okay, but it could be.
L2 tensor element.
Like that. And same thing up here. That's L. Okay, so what does this dimension simplify out to, and what does this dimension simplify out to?
That's just L2 inverse on the top and L1 inverse on the bottom.
Right, because this L1 inverse cancels out with this L1 here. It's giving us L2 inverse on top, right? And same basic idea is this L1 inverse on the bottom. So that's telling us where we should put these generators, X and Y.
You're using language a little bit by still calling it X and Y, but I'll finish.
Yes, but it's not that much confused.
No, I'm just
Okay.
telling the people out there watching this are
Sure. Sure. So where is X going to live? X is going to live over here. So the generator X right there? No. The generator X lives right there. The generator Y lives right there. And well, so I guess we'll finish up with this example for now, and then we'll try to do some more examples next time, and we'll try to learn some more doctrines, some more of the relevant doctrines in algebraic geometry next time. And if you want to think about this example, work out more details out if you can. It's a little bit fun. It's also very simple in a way. If you change n into something higher, like n equals 3 or something like that, you might find it more of an interesting moduli space to explore. But all right, let's quit there.